I confess physics is not my long suit, but I think I can understand this one. Conservation of energy. One of the most important laws of physics is the law of conservation of energy, discovered by Michael Faraday, and that's not the same guy who's in the Lost series. It can be derived from the fundamental theorem of line integrals. Actually, that's theorem 15.5. So from physics, the kinetic energy of a particle of mass m and speed v is 1/2 m times the square of the velocity. The potential energy P of a particle at point xyz in a conservative vector field is defined as P of xyz, which is the negative of f of xyz, where f of xyz is the potential function for the vector field f. Okay, consequently, the work done by a force F along a smooth curve C from point A to point B is the line integral f dot dr over curve C, which is the potential function evaluated at B minus the potential function evaluated at A, point A. This is point B, point A, which is the negative of the potential function of at the same point evaluated at B and evaluated at A. And notice the negative sign here and the flip. This is now P of A minus P of B, as opposed to P of B minus P of A because of this negative sign. So in other words, the work is equal to the difference in the potential energies of A and B. And if we suppose then the vector value function R of t is at the position, or is a position vector for a particle moving along a curve C from point A, which is R of A, to point B, which is R of B, then by Newton's second law of motion, F equals mass times acceleration, which is mass times the derivative of the velocity, which you knew that from Calc 1, where F, A, and V prime are vector value functions. So we got an acceleration vector, a velocity vector. Actually, A and V prime are the same. And F is a vector field. The work done by the vector field moving a particle from point A to B can be expressed as the integral of f dot r prime dt, or the integral of f dot velocity vector times dt. And so another way to do that, of course, is, since we got force times velocity vector integrating m times a of t times, or dot I should say, times the velocity vector dt. Remember, recalling that f is m times a, so there's that part, and here's the velocity vector times dt. This is actually a dot product, and this is times dt. Actually, the dt is just part of the integral. And so, when we do that, we get 1/2 as a constant times the derivative of the velocity vector dotted with itself, dt, integral going from A to B. So, from the fundamental theorem of calculus, when you integrate a derivative, you just get the function itself. So, the work done is mass over 2 times the length of the velocity vector evaluated between A and B. So even, we're still at it, eventually, 1/2 times mass times the velocity vector squared. See, the length of it squared. That's the, oh wait, we got this with itself. We find the length of it squared. So velocity vector squared, evaluated between A and B, and finally, the whole point is trying to get to this. Some function k of B minus some function k of A. And equating the results were done both ways. Then the P of A minus P of B is some k of B minus some k of A. So with a little algebra we can see that P of A plus k of A, the potential energy plus the kinetic energy, at a point is equal to the potential energy plus the kinetic energy at another point. So the sum of the potential and kinetic energies remains constant from point to point when the vector field F is conservative. An example: toss a ball in the air at the beginning of the flight. The ball has only kinetic energy. That's all. No potential. At the top of its flight, the kinetic is 0, but the potential is all the ball has. But if you add the potential plus the kinetic, it's constant during the entire thing. So at the points between the sum of the kinetic and potential is always the same. Recall, gravitation fields are conservative inverse square fields, right? Oh, physics is a weakness of mine. I hope you could understand that.
Nice work.
Thanks.